Okay, good morning students. Now we are going to study about numerical based on Bohr's theory. Okay. Numerical based on Bohr's model of atom. Okay, first we are going to solve the problems. In this first problem, you see what I am telling, that what is the wavelength of light emitter when an electron in an hydrogen atom undergoes transition from energy level n is equals to 4 to energy level n is equals to 4 to energy level n is equals to 1. You see, now you are reading once again, what is the wavelength? Means what they are asking there, to find the wavelength given, to find out wavelength of the light, means lambda is equals to question mark emitter when electrons from hydrogen atom, they giving the atom is also called as hydrogen atom, undergoes transition from N4 to N1. You see, energy is coming from N4 to N1. See, N is equals to 1, N is equals to 2, N is equals to 3, N is equals to 4. Okay, energy coming from 4 to 1. Okay, means they given N1 is nothing but 1, N2 will get 4. They given. We know the formula 1 by lambda by Balmer's equation. Balmer's equation, they given that R is equals to 1 by n minus n1 square minus 1 by n2 square. We know R value, it is Raber constant. R is nothing but Raber constant. R is equals to 10967 per centimeter. You know that. We know that previous class only, while studying about wave nature, wave number is nothing but 1 by lambda. We know this formula, correct? No? Then we can find that 1 by lambda, correct? No? I'm going to write 1 by lambda is equals to, we have the formula wave number is equals to 1 by lambda. We can do in two methods in this problem, while using this formula, or we can use this formula. Okay, first we will take this formula only. 1 by lambda is equals to, we know the Raber's value, that is 10967 into 1 by n1 square is nothing but 1 square minus 1 divided by, what is n2 is 4 square. 4 square is nothing but 16. If you calculate this, we will get 1 by lambda is equals to 10281.56 per centimeters. If you want to find out lambda, we can do lambda is equals to 1 divided by 10281.56 per centimeter. We will get 0.00009726 per centimeter. If we go to upper side, become plus. Okay, we want to do lambda, we can do substitutions, taking to power 9.7 into 10 to the power of minus 6 centimeters. If you want to keep in centimeters, it's okay, or we can keep in nanometers. Lambda is equals to 97 into 97 nanometers. So one method. Another method is there. It is a frequency, mu bar equals 1 by lambda. It is nothing but wave number. We can find like this method also. Mu equals, similarly same steps will be here, 0.9677 into 1 by 1 square minus 1 by 4 square. We will get the value 10281.5 per centimeters mu bar. We know the formula. Mu bar is nothing but 1 by lambda. Mu bar is equals to 1 by lambda. We can find out lambda is equals to 1 by mu. Similarly, 1 by is equals to 102.815 per centimeters. We will get 9.7 into 10 to the power of minus 6 centimeters. We can keep in nanometers, 97 nanometers. By this method we can do this problem, while the two taking a wave number, or we can straightly we can do 1 by lambda. So two methods we can solve this problem. Okay, yes students, next we are going to second question. Calculate the wavelength of the first and last line in the Balmer series of hydrogen spectrum. You see what they're telling. Calculate the wavelength means given we want to find out what wavelength we want to find out, correct? No, then first and last line are in Balmer series. We know if you talk about a Balmer, they given Balmer. No, in Balmer the stationary or initial n1 is equals to 2, n2 is equals to 3, but they are telling that first and last line. First line is n1 is equals to 2 only, n2 is nothing but infinity. We will take infinity. Okay, we know the formula by Balmer equations. 1 by lambda is equals to Rayber constant, or 1 by n1 square minus 1 by n2 square, correct? No, we want to apply for both. First we apply for this while dividing in 2. Okay, we'll take first 1 by lambda is equals to 10967 into 1 by 2 to the power of 2 minus 1 by 3 square. If you substitute this value, we will get 1 by lambda is equals to 152329 per centimeter. If you convert it into lambda, means lambda is equals to 1 by 152329 per centimeters. We will get 6.565 into 10 to the power of minus 5 centimeters lambda. Okay, this is for we'll taking Balmer. But what they asking that first and last line we don't know. For that we taking infinity. While infinity orbitals are the coming from two first orbitals, correct? No, 1 by lambda is equals to 10967 equals 1 by n1 is nothing but 2 square minus 1 divided by infinity. We know that 1 by infinity is nothing but 0, correct? No, then 1 by lambda equals, if you substitute 0, overall substitutions we get 274,195 per centimeters. If you convert it into lambda is equals to 1.1 by 274,195 per centimeters. We will get 3.647 into 10 to the power of minus 5 centimeters. This is lambda wavelength. You see, calculating the wavelength of first and last line in the Balmer series. While Balmer series starting from 2 and 3, correct? No, while come to, they are telling the first and last line. We don't know the last line. For that purpose only we taken the infinity another. I am taking that both the answers. Okay, by substituting 2 and 3 and 2 and infinity, we got this answer. Okay. Problem. Applying Bohr's model, calculate the wavelength of the radiation emitter when an electrons in hydrogen atom make transition from fourth energy level to first energy level. They are given the Planck's constant H is equals to 6.63 into 10 to the power of minus 34 joules second. Okay, joules per second. You see, applying Bohr's model. Okay, applying Bohr's model, calculate the wavelength. Means they given to find out wavelength, correct, no, of the radiation emitter when an electron in hydrogen atom make transition from fourth means they're giving that n values, correct, no, n fourth energy level to first energy level. N1 is nothing but 1, N2 is nothing but 4. Okay, fourth energy level to first energy level. Planck's constant H is equal to 6.623 into 10 to the power of minus 34 joules per second. We have the formula energy of nth orbital. Energy of nth orbital En is equals to 2.18 into 10 to the power of minus 18 by n square joules per atom. This is the formula. This formula we can see in further videos. I will solve it. How we will get the 2.18. Okay. This is the formula. You see, first they are telling that n is nothing but 1. Correct? No. While substituting n is equals to 1, what we will get, and n is equals to 4, what we will get. Okay. We are substituting energy in nth. No. Now we are telling energy in first orbital. Okay. First orbital is equals to 2.18 into 10 to the power of minus 18 by n is nothing but 1 square. N is equals to 1 square. Another energy of fourth orbital, fourth energy level, 4 square. Okay, this is what we got. We know that energy E is equals to 2.18 into 10 to the power of minus 18. We can write 1 by 1 square by minus 1 by 4 square. Correct? No? How can we write this? By using change energy is equals to E1 minus E2, where here we tell that E1 minus E4. Okay, while energy, while 2.18 we take a common, we get this formula. Okay, you see, overall what we'll get, delta E is equals to, if we substitute the values, we'll get delta E is equals to change minus 2.04 into 10 to the power of minus 18 joules per atom. Joules per atom. We have the formula. First only we studied about E is equals to H nu. Correct? No? E is equals to H nu, or we can write nu is equals to C by lambda also. Correct? No? If you substitute nu is equals to C by lambda in E is equals to H nu, we will get HC by lambda. HC by lambda. We want to find out wavelength or lambda. Lambda is equals to HC by E. HC by E. We got the E value. We got Planck's constant value. They given 6.63 into 10 to the power of minus 34 joules per second. C is nothing but velocity of light. If you substitute, we'll get lambda is equals to 6.63 into 10 to the power of minus 34 joules per second into velocity of light 3 into 10 to the power of 8 meter per second divided by energy. What the energy we got? Minus 2.04 into 10 to the power of minus 18 joules per atom. Joules per atom. If we substitute, we'll get lambda is equals to 9.7 into 10 to the power of 8 centimeter. If we shift the decimal, we'll get lambda is equals to, or we convert it into centimeters to nanometers, will get 97 nanometers. We'll get the lambda. You see what we taken. They told that applying the Bohr's model, calculate the wavelength of the radiation emitter, means emitting. When electrons in, means you see, if you take an orbital, sorry, the diagram is first. I'm writing here nucleus, first orbital, second orbital, third orbital, fourth orbital. What they're telling, when an electron in hydrogen atom makes transition from fourth energy level to first energy level, means you see this is 4, correct? No, 4 to first orbital. First orbital, wavelength of the radiation emitter, means it will absorb and also emitter. For that only we talk emitting is nothing but photons. Okay, while the photons in the Planck's constant. Okay, that energy is nothing but 6.623. Okay, overall, what is the wavelength? Wavelength from N1 to N4 is nothing but 97 nanometers. Okay. Last problem by the Bohr's model. We can go through these many textbooks or NCERT textbooks. I solved that questions. You see what is the last question? Calculate the wavelength for the emission transition if it starts from the orbital having a radius. You see, they're giving the radius of the orbital. For they given that 1.3225 nanometers, 1.3225 nanometers, and end at, you see, and end at 211.6 picometers. They changed the units. You see, you want to please while solving the problem, you want to go through the question properly, or else you cannot solve the problems. Name the series. They are asking that series also to which transition belongs and region of the spectrum. They are asking that. You see, given calculate the wavelength. Okay. For the emission spectrum and started from the orbital having the radius 1.3225 nanometers and the end at the 211.6 picometers. Name the series. They are asking that series also and series to which transition belongs and region also, which region it belongs. They are asking 3. We want to find out. Okay. While coming to the what they given, first lambda they given, and they given that the orbit having radius, means they giving that radius 1 equals, because they given first radius now 1.3225 nanometers. Nanometers is converted into picometers. 13225 picometers. This is R1 radius. Second, what they given, R2 radius is 211.6 picometers. They are given the 2 radius. You see, the previous problem we studied about energy of nth orbital formula. Now we are going to study about radius of nth orbitals. Okay. Is nothing but Rn is equals to 52.9 n square by Z. Z is nothing but hydrogen atomic number. Okay, Z. This is the formula. Please, you want to clarify the formula, because the formula is very, very important. We will see this formula in next videos. Okay. Similarly, what I told in third problem, similarly in fourth problem also, the radius of nth orbital will be seen in next problems. While studying in quantum mechanics, we'll know the formula. Okay. You see, we know that R1 by R2 equals, what we'll get, 13225 picometers divided by 2116 picometers. We can also write this is n1 square by n2 square. Correct? Now, if you substitute this value, we'll get 6.25 n1 square by n2 square. See, square, if you take square to left side, we'll get square. It was 6.25 square, we'll get 2.5 n1 by n2. Okay, we got n1 by n2. 2.5 means we can write this 25 by 10 equals n1 by n2. We can do 5 5 is 5 2 is we'll get the value n is equals to 5, n2 is equals to 2. While we know that every time the n1 value must be a least, n2 must be a higher, but here we're getting a oppositely. For that we'll change this, while cross multiplications we'll take n1 is equals to 2, n2 is nothing but 5. We have the Balmer series formula. 1 by lambda is equals to r 1 by n1 square minus n2 square. We know that Reiber constant 1096, sorry, we converted into nanometers, 1.097677 into 10 to the power of minus 7 into 1 by n1 is nothing but 2 square, n2 is nothing but 5 square. While substituting, we will get this 2.303 into 10 to the power of minus 6 meters. If you want to we want to find out lambda, no, lambda is equals to 1 divided by 2.303 into 10 to the power of minus 6 meters. We will get lambda is equals to 0.434 into 10 to the power of 6 meters. If you convert it into nanometers, 434 nanometers. See, lambda we got 434 nanometers. We got the 434 nanometers. We know that lambda 434 nanometers means the visible region. We'll come to electromagnetic radiation. Electromagnetic radiation. I explained that gamma rays, X-rays, UV, visible, infrared, X-ray. The visible region is 400 nanometers to 750 nanometers. Then it is the lambda, what we getting the wavelength 434. Then it is what this, it is visible region. It is, we got visible region. We got visible region series. You see which series it is, Lahmann, Balmer and Paston or Pfund or bracket, which series it is. You see, already I told this, n1 and n1 is 2 and n2 is 5. We know that Balmer will start from n2 only. Then it is Balmer series. We have find out that Balmer series also, visible region also. You see, once again I am explaining this problem. Calculating the lambda of the emission transition. Emission transition means calculate the wavelength for the emission transition if it starts from the orbital having the radius 1.3225 nanometers and end at the 211.6 picometers. Name the series to which the transition belongs and the energy of the spectrum. They give we want to find out wavelength, we want to find out series, we want to find region. They given the radius is 1.3225 nanometers. We convert it into picometers. R1 radius is equals to 13225 picometers. R2 is equals to 211.6 picometers. Radius of the nth orbital formula, we know that Rn is equals to 52.9 n square by z. While substituting this for R1 and R2, we'll get this R1 is equals to 13225 picometers. R2 is equals to 211.6 picometers. While substituting, we'll get 6.25 is equals to n1 square by n2 square. While squaring to 6.25, we'll get 2.5 is equals to n1 divided by n2. While 2.5, we can write that 25 by 10, correct? No, 25 by 10. If you see 25 by 10, it will get 2.5 only. For that only I taken the 25 by 10. While substituting 5 by 2, n1 is equals to 5, n2 is equals to 2. While we know that every series must be starting series or first orbital must be lesser compared to I. For that n1 is equals to 2, n2 is equals to 5. While here only we can find out this, it is Balmer. It is Balmer because n1 is equals to n1 is equals to 2 means it is a Balmer series. Okay. Next we are applying that Balmer equations. Balmer equations is equals to r 1 by lambda is equals to r into 1 by n1 square minus 1 by n2 square. While r is nothing but Reiber constant, if you substitute in the formula, and n1 is nothing but we know that 2, n2 is nothing but 5. We substituted here, we got 1 by lambda is equals to 2.303 into 10 to the power of minus 6 meters. Well, we want to find out lambda is equals to 1 divided by 2.303 into 10 to the power of minus 6 meters. We get 0.434 into 10 to the power of 6 meters. If you if you convert it into nanometers, lambda is equals to 434 nanometers. While electromagnetic radiations, I already told that gamma, X-ray, UV, visible, infrared X-rays, the visible region is 400 to 715 nanometers. Then it is the region wavelength 434 nanometers. You see, it is a visible region. Okay. Next topic we are going to study about quantum number. Okay.